Okay, Professor Jose Antonio, the floor is yours, my friend. So I think that you can talk, you can present yourself. Jose is a great engineer working for satellites, TinyML inside satellites. So it's a pleasure to have him here. And also Jose works with Arduino.
Okay, thank you, Marcelo. And hi, everyone. My name is Jose. I'm going to start my presentation. So just confirm me if you can see it. Yes. Okay, cool.
Yes.
So let's start with this session. This session is called Advanced Anomaly Detection with Edge Impulse and Arduino. My name is Jose. I am a professor and also a researcher from Universidad del Valle de Guatemala in Central America. And basically, my work with TinyML is related with nanosatellites. I work at the aerospace laboratory here at Universidad del Valle, and something we have been planning and have been working on is to implement TinyML on these nanosatellites that are called CubeSats, and to improve the way they work on space, basically. I have here one CubeSat, a representation of a CubeSat. This is a CubeSat. This is a 1U CubeSat. So our research and our idea and our proposal is to put TinyML inside this, so we can take better decisions in space when the satellite is in space. So that's basically my work that is related with TinyML. On this session, what we are going to cover, we are going to define what is an anomaly detection. We are going to talk about some practical use cases, and we are going to end with a hands-on demonstration of Edge Impulse and Arduino working as a team for implementing a TinyML model, a really simple TinyML model. Okay? So please, let's make this. Please ask, chat, use the Zoom chat. Let's make this like really something on which we can participate all. So please let me your questions on the Zoom chat if you have any. As I told you about me, besides my work at the university, I also work at Arduino. I am part of the product experience team, and basically my work is related with content creation. But besides Arduino and satellites, I really enjoy hiking, as you can see in the image on the left. I am in the highest peak of Guatemala. It's called Volcán Tajumulco, and at the right is my new addition, my new Arduino board that it's called Milo, and it's my dog, and I also spend a lot of time with him, and basically he's my TinyML companion. Um, okay, so let's talk about anomaly detection. Anomaly detection is defined as the process of identifying patterns, events, or data points that deviate significantly from expected norms. Um, Anomaly detection is really important in a lot of fields. We can talk about finance, cybersecurity, healthcare, but in this hands-on, we are going to focus on industrial equipment monitoring. That it's something that it's very related to anomaly detection, and it's very useful in the real life. Let me tell you that there's a lot of examples of real life examples that they they are already using anomaly detection, and those anomaly detection models can be improved a lot with the use of TinyML. So why is important anomaly detection in industrial equipment? Basically, I have identified 4 points. We can talk about early detection. For example, if you want to detect an failure way ahead of time it happens, anomaly detection can help you with that. Also with efficiency improvement, if you want to improve efficiency of how your equipment work, you can also use anomaly detection techniques. Also super important is safety. Safety is also super important in industrial environments. We can also use anomaly detection models and techniques to improve safety on industrial ecosystems. And also, I think one of the most important anomaly detections application is predictive maintenance. So we want always in industry, we want to save some money. And the way to save money is to give the right maintenance to equipments that are working. Okay. So if you know more important aspects of anomaly detection, please share them in the Zoom chat. Those are the four I thought about it. But if you have any other example, please share it on the Zoom chat. It will be really awesome to have more examples of why anomaly detection is important in industrial equipment. Also, some use cases of anomaly detection in industrial equipment are the following: vibration analysis and bearing fault detection, temperature monitoring and overheating detection, also pressure monitoring in pipeline and vessels, energy consumption analysis, and acoustic emissions and ultrasonic testing. We're going to focus right now on a simple vibration analysis and we are going to implement that vibration analysis on a fan, basically. Um, why a fan? Basically because a fan is easy to interact with, and also it's easy to make tests with a fan. I'm going to show you right now what I am going to do with to test a fan, to simulate a fan that you can find these fans basically everywhere in industrial ambience. For example, if you are working on a cold room, you can find fans. Also, in those big warehouses, they have fans. And in a lot of context, fans are really an important part of a lot of process. So knowing that the fan is working okay, it's crucial for a lot of process. Okay. So basically, the hands-on propose the following. We are going to use a cheap computer fan to simulate that industrial fan. So right now I'm going to do something. I'm going to stop sharing my presentation and I'm going to change my webcam. And I'm going to show you if you can put yeah. I'm going to show you the test rig for today. So as you can see here, you can see the fan. I have designed this 3D printed case and stand for the fan. This is a quite simple and cheap fan that you can find like basically in any computer store. And to the fan, to this fan case, I just attach an Arduino Nano Sense BLE board that we are going to use to make the anomaly detection model. Okay. There are another Arduino boards that you can use for this. For example, I have here the Nikla Voice. That this one has an IMU also. You can see the size of this board. You can also use these boards, or you can also use another different type of board. It doesn't need to be Arduino. You can use, for example, ESP32 and with a standalone accelerometer. Yeah, basically you can use everything. I can share you these files if you want to make the tests, and yeah, and you can print it and make the test in your house. So yeah, don't worry. I'm going to share that in a minute with Marcelo and also with Marco. Okay. So I also have another question. Do you think that the placement of the accelerometer on the fan matters? And share your thoughts on the Zoom chat. Basically, I share it on the I put the accelerometer right in the axis of the fan, but we can put the nano board basically in a lot of places of the fan. So if you have another suggestion to put the fan, please also let your thoughts on the Zoom chat, please. Okay, so continuing with the presentation, we're going to use the Arduino Nano 33 BLE Sense. It's a quite long name for a really great board. This is a compact and versatile development board from Arduino. It is based on a Nordic semiconductor microcontroller, a really powerful microcontroller. And the board basically is designed for low power applications that need to interact a lot with the environment. It features Bluetooth low energy connectivity, so it makes that feature make this board also ideal for wireless projects. But also, this board has 11 onboard sensors. Like it's a lot of sensors that this board has. The microcontroller is a 32-bit ARM Cortex M4 processor. It has 1 megabyte of flash and 256 kilobyte of RAM. The connectivity, as I told you, it has BLE connectivity, and the sensors, it's 11 sensors in total. It has a 9-axis IMU. It has also a temperature, humidity, and also a barometer, a digital microphone, a gesture, proximity, and ambient light sensors, and a color sensor. It has 11 sensors in total. This really small board, like you saw in my camera that it's a really small board, but it's packed with 11 sensors, 11 different sensors. So it's a nice board. In my opinion, it's one of the best boards that Arduino has right now. So we are going to use this board for this hands-on. And an important note, I think this is important to talk about. Right now, there are two versions of this board that these two versions are called Rev 1 and Rev 2. There are there are important differences between the two versions, and those differences are that each board has a different IMU, also different temperature and humidity sensors, and also different microphones. So Edge Impulse firmware, it works right now with both versions, but probably you are going to encounter problems when you are working with the Arduino IDE. So be sure and double check that you are using the correct version while working on the Arduino IDE. And that's basically just um, noting what revision of the board you have and importing the right libraries, as I will show you on the hands-on. But right now, Edge Impulse firmware is compatible with both versions, and also the Arduino IDE is compatible. You just have to be aware of what version you are working with. Okay, talking about Edge Impulse, basically Edge Impulse configuration can be divided into 4 main steps. You have to install the CLI, the CLI. You also have to make an account on Edge Impulse. Making accounts on Edge Impulse, it's free. There are also enterprises plans, but for now it's free, and the free plan of Edge Impulse is quite good for a lot of applications. So you don't need the enterprise application, the enterprise feature. Then you have to install the Arduino CLI or the Arduino CLI installation, and also you have to install the latest Edge Impulse firmware to the board. Basically, what you have to do is to I'm going to show you right now. It's just to follow. You just have to follow um, the following instructions that are quite nice explained on the Edge Impulse documentation site. I'm going to leave. This is also in the presentation that I'm going to share with you, but I'm going to also share it on the Zoom chat if you want to see it right now. Basically, as I told you, it's four main steps you have to do in order to install Edge Impulse in your computers. Okay. And a small note about this is that Edge Impulse installations can be a little bit tricky. So don't hesitate to send your questions to the network Discord server. So the people like me that we have a lot of experience installing the Edge Impulse, we can help you with this. But don't worry, it can be tricky for some computers and it cannot be tricky for other computers. But if you encounter some errors, please just put your questions on the Discord server. And I think there's a lot of people that can help you with the installation process. Okay. So after talking about Edge Impulse a little bit, well, Sean gave you an awesome presentation about Edge Impulse. And after also talking about a little bit about anomaly detection and what we are going to do, let's see how to make and how to train models using a board, an Arduino board in this case, and also Edge Impulse. So what I am going to do now is just show you, as you can see here, I have this anomaly detection project. Um, Also, this is public, and you can access, and you can use the data, and you can see all the what are I am going to show you right now, but you can use it after if you want some guidelines and some guide to make an Edge Impulse model. So basically, when you enter Edge Impulse, you have all of these options. You have this landing page. And the first thing I'm going to do is to connect the device. As you can see, connecting a device is really simple. Well, right now I'm going to disconnect the device. And what I'm going to do is to open Node.js. Edge Impulse works with Node.js. And basically, you have to connect your Arduino board and then open the Edge Impulse daemon. This is a serial client of Edge Impulse. And basically, what you have to do is to put your account, connect your board, and the serial daemon is going to automatically connect your board to Edge Impulse, to your Edge Impulse account. So as you can see, my device is now connected to data acquisition. So I have now a board connected to my Edge Impulse account, and I can use that board from my Edge Impulse account. Okay, so that's a really nice feature in my opinion. And as BJ talked yesterday, and also Marco talked yesterday, probably what is the hardest thing to do when training a TinyML model is to get data, and not only getting like high quality data, but also the process of getting data can be tricky. But Edge Impulse make it really easy. Like you just connect your board, you have it connected to your account, and now let's go to data acquisition. Okay, so here in data acquisition, you can see that I have already some samples that I take some minutes ago. I was just making some tests. You can see here two labels. I'm going to show you how you can take data and how you can record data. So basically, it's quite easy and quite straightforward. You just have to connect to the board, to your board. So I have the SciTinyML-2024 board connected. So this is my device right now. I am going to make a test right now with the fan, turned off. I'm going to take a 10-second sample, and I'm going to use the IMU. I am going to use the IMU sensor of the board. I can also use the built-in microphone. I can also use the color, brightness, proximity gesture, and the inertial and interactional sensors. I can use all the sensors from the board. But right now, we are just going to focus on the inertial, that it's the IMU, the accelerometer, the gyroscope, and the magnetometer. And the frequency, we are going to leave the frequency, the sample frequency at 100 hertz. So it's simple as just pressing the start sampling. And if everything is okay with my board and my connection, you are going to see that the sampling starts. And then when it is finished and when the sample is uploaded to your H Impulse account, you can see and you can right now, yeah. So this is the last sample that I just record. Now I am going to record a new sample with the bot with the fan working on. So I am going to change my camera so you can see the fan working. I have the fan working there. I have the fan turned off here. Okay, so I just want you to see that the fan is working now right now. So fan working, and I'm going to start sampling. Okay. So let's wait 10 seconds of samples. And we can expect a different graph that is going to be shown right now. It just takes some time. Um, okay, yeah. So you can see here that this is the data from the fan working. As you can see, as expected, we can see that the magnetometers are measuring uh, the magnetic fields produced by the motors, and we can see also the accelerometer um, um, readings. Okay, what do you have on the y-axis for this sensor data collection? Oh, on the y-axis, it's G's, and also I don't remember I think it's micro Teslas, or well, I have to confirm that. Okay, but yeah, it's basically the y-axis is related to the sensors. Okay, so as you can see, uploading data to H Impulse, it's really easy. Like you just have to basically to connect your board and upload data, and yeah, and start sampling data. But also you can upload data, existing data. For example, if you press here, you can select individual files, or also you can select a folder. And well, it's a quite nice platform that lets you use your own data or to sample directly your data. Okay. So I'm going to return to the presentation and just talk about some general guidelines and a general workflow that we can follow for developing an anomaly detection model. Um, the workflow can be divided into 5 important steps. The first is data collection. Aim for at least several hundreds of samples per class to start. In this example, we are going to, this is a really simple example, so we are not going to use hundreds of samples. We are just going to use 6 minutes of recordings of data. It's just for demonstration purposes, but for a real life scenario, we have to, well, it depends on the model, but we have to record a lot of more samples. After data collection, you have to pre-process data. This is a really important step. You have to ensure that data is suitable for training and a machine learning model. And that is related to what BJ and also Marco were telling you, and also Marcelo were telling you yesterday in the talks, that probably the most important part of developing a TinyML model is the data collection and also the data pre-processing. Okay, then you pass to a next step, that is model training. In this step, you have to split your data into training, test, and validation sets. A common split ratio is 70% for training and 30% for testing. I think that H Impulse uses the 80-20, 80 for training and 20 for testing. Okay, so this is an important step also. Then you have to evaluate your model to understand how well the model is performing. And for the last step is the model deployment. So we're going to see every part of this workflow right now on this hands-on. So let's remember about this and let's have present this workflow. Okay, and as I told you, we are going to gather two different types of samples. The first is idle and the second is nominal. Okay, other classes like broken or obstructed are not necessary but can be added to improve the model significantly. So as you can see here, I have already gathered the idle. You can see the idle is when the fan is turned off, and I have here the nominal. Okay, nominal is when the fan is turned on. I have 24 sets recordings for training, and I have 14. Well, right now it's 14. I was making some tests, but initially I had 12 recordings for testing, and you can see here the train test split. Okay, so for this model, I am just using 70 and 30% for splitting my data. Okay. And as you can see, I have 6 minutes of data collected. So the first step of this of this workflow, we just made it with Edge Impulse. And as I told you, you can upload your data also, or you can work directly from the Edge Impulse account. Now, let's pass to the Edge Impulse design. Well, I'm going to make some changes here. I'm just going to show you how it's the workflow. Um, so when you start working on the impulse, you have to add an input block. I am going to add a time series data, and I'm going to change the windows. Well, you can see that time series data. Right now we have 9 measurements. We are going to change the window size to 200 milliseconds and to 100 on the window increase. Basically, the window size is the the time of the interval of data of data you are going to use to train the model. Okay, and the window increase is how you are moving the window to make the training. We are going to use the frequency of the 100 hertz, basically the frequency that we use to record the data. Processing blocks, we are going to add an spectral analysis block. Okay, we can use all the measurements, but in this case, we're just focusing on the accelerometer measurements. Okay, so I am not selecting the gyroscope and the magnetometer. I am just going to focus right now on vibration. That it's basically what the accelerometer tell us about. I am going to add 2 blocks. I'm going to add a classification block and also add anomaly detection k-means block. Okay, so with the first block, we are going to be able to classify the data into idle or nominal. And with the anomaly detection block, we are going to be able to identify when an anomaly is happening in our system. Okay, we save the impulse, and now we go to the spectral features. Okay, basically the spectral features, Sean talked about this. I'm going to leave the default parameters right now, but you can work, as you can see, there's a lot of parameters that can be tuned, depending on your model and depending on your application, you can change the spectral features and the spectral parameters. I'm just going to save these parameters right now, and I'm going to generate the features. It's important to calculate the feature importance, and I'm going to right now remember that this is cloud-based. So we just have to wait a little bit to edge impulse to finish. Oh, sorry, I'm just wait. Sorry. I don't remember where I put something. Sorry. Oh, I think I don't have it on this slide. But I'm going to search it later. Let's just wait a little bit. It's a really simple model, so um, it shouldn't take a lot of time. So just be patient a little bit and let's wait. If you have some questions right now, I think it's the time to answer some question. Could you tell us if you have tried TinyML with Raspberry Pi boards and any model? Yes, I have tried. TinyML works well, as Marcelo say. TinyML works really well on Raspberry Pi models. Okay, you can see here the result of the feature generation and the training. You can see that this is what we expect. We expect that idle and nominal that are really apart from them. Something that will be bad will have been having the idle and nominal together, but right now it's quite separated, so it's good right now. Okay. You can see that also edge impulse measures an on-device performance. We have a processing time of 3 milliseconds, and also we have an estimated peak RAM usage that it's 1,000 bytes approximately. Okay. Then we are going to train the classifier. Also, you can work here and you can modify the neural network settings so it can you can set it depending on your model and your application. So I'm going to start the training right now. And also let's wait some minutes. It's quite a simple model, so it shouldn't take a lot of time. If you know a lot of neural networks, you can work here a lot. Like you can work a lot with the neural network. You can even work on switch to an expert mode and work on the code on written code. But if you are if you are new to TinyML and machine learning in general, you can trust in the default parameters of that edge impulse proposes, and after making tests, you can like improve your model. And that's what makes, in my opinion, edge impulse really nice, that you have a lot of help from the site, from the platform, and it can save you a lot of time, and also you can learn a lot. Okay. So we have the results here. An important note is that the accuracy it's 100%. This is not you probably you can think this is okay, but this is not really okay. Right now we have a 100% of accuracy because of the model, because it's really small. We have a like 6 minutes of data. It's a really small model just for demonstration purposes, but in real life you are not getting 100% of accuracy. Yeah, and that's okay. Um, Basically, you have to work with what what it's good for you. Okay, so don't expect in real life to have 100% of accuracy. And if you have 100% of accuracy, it's probably because you don't have a lot of data, or you have something that must be changed in your model. Okay. We also can see an approximately on-device performance. You can see an inference in time of 1 milliseconds, the peak RAM usage, and the flash usage. This is also really nice, a nice feature of Edge Impulse, and can give you a lot of a good idea of the computational resources you are going to use from your board. And that is really an important thing to validate. Um, also be when you are working on devices that are going to work in the in the field, like to know how well they are going to work. And I'm going to show you a real life example at the end of the presentation that I work in some years ago. Okay, so we have the classifier done, and now we just have to train the anomaly detection model. I am going to select the suggested access. As you can see, there's a lot of features that you can use. I'm going to select the suggested access from Edge Impulse right now and start the training. And uh, after that, we are ready to make some tests and to deploy the model. Okay. Okay. I'm going to go back to the presentation really quick and just talk about some important steps. Some comments about data collection is that well, in this hands-on we use 6 minutes of data, and for training we did the 70-30% training split, the split ratio. Sorry, we use 4 minutes for training and we use 2 minutes for testing. Okay. Also, an important note for the number of samples required for an anomaly detection model. There is no one size fits all answer, and this is really important. There are some general guidelines that can determine an appropriate size of sampling, but there is not a one size fits all answer. It depends on your model and it depends on your application. So, for example, with complex patterns in terms of data, you need larger sample sizes. Also, depending on the type of anomaly detection technique you are using, for example, supervised set methods require more samples than unsupervised set methods. Also, model performance, more data is not always better. We used to tend you used to tend to think that having a lot of data it's better, and as BA told us yesterday, sometimes we even break the internet trying to get a lot of data, and it's not always the better. And also, depending on the rarity of the anomalies you are trying to identify, probably if those anomalies are quite rare, you are going to need a larger sample size. But a starting point is consider collecting at least several hundred to a few thousand samples to start um, a training to start training a model. Okay, as I said, no one size fits all answer. Um, okay, also, comments about pre-processing data. We can achieve a more accurate model in less time by standardizing and decorrelating input data. I have shared a great paper about that. And also there's a Google Colab notebook from Sean and also from the Edge Impulse team that I'm going to share you also in this presentation. Okay, I'm going to go back to to Edge Impulse. As you can see, this is the result of the anomaly explorer and the anomaly training. This is the what we were expecting, basically having this like clouds covering all the data, all the samples. So right now it's time to test the model. Testing the model, it's quite easy also in Edge Input. You just have to go to the model testing option. And well, we are going to test test it live. So I'm going to use the live classification option. I'm going to use the board I have connected to my account. Right now the fan is turned on, and I'm going to start sampling 10 seconds of data. Okay, so what we expect right now is that the model says that the fan is on, is turned on. Okay, so okay, we're using the model we just trained it, and let's wait. It's classifying the test, and you can see the scores. You can see that as expected, the model identifies that the fan is working as nominal. Okay, you can see that the when the score is more is it's one, it's because it's what we expect, and idle it's not turned off. Okay, I'm going to shut down the fan right now, and I'm going to start sampling again. I just want you to see what happens. The sampling started right now. 7, 6, 5, 4, 3, 2, 1. Okay. The fan is turned off. And let's wait for the classifying. And you can see that as we expected, idle right now. The fan is turned off. Okay. So the probability of or the score, it's higher in the idle. It's what we expect. And right now, I'm going to turn on the fan, but if you can see my camera, I'm going to try to make some anomaly, but I don't want to lose my finger, so just give me a second. I'm going to try to put something in the fan, blocking the fan. I'm going to start sampling, and let's see what the model says. Okay, so we have the test data, and it says it's nominal. So as you can see, we have an anomaly score sometimes that it's not negative, it's positive. So yeah, it's working nominal, but probably there's an anomaly. As you can see, there's the anomaly score, it tends to grow up, okay? What I can see from this really uh really simple test and model is that in order to identify better the anomaly, probably I have to improve my testing my testing set. Okay, and this is what makes TinyML also like really cool. That you have to test a lot. You have to gather a lot of data, and yeah, it's quite fun to make the models work as you expect. What if you have the fan off and then starting rotating by hand? Okay, let's make that. Yeah, we can test that. Why not? Going to start the. I don't know if I can make that, but I'm just moving this, sampling. I'm just moving it with my finger, and let's just wait. Yeah, we have 85 anomalies, 13 idle, 1 nominal. Yeah, probably something bad is happening right here, right? Okay. So as you can see, like
Jose,
in
Jose,
yeah,
there is a question from where people can see the anomaly. I think that you can see the samples outside of the clusters in the anomaly explorer, no? Here
yeah,
in the below.
yeah,
Yeah. So though all those points, the orange points that test the data is outside of the cluster. So it means that there are anomalies.
yeah. You
Yeah,
expect the in nominal and idle conditions, you expect the samples to be inside these like clouds. But when something is outside the clouds, that is considered as an anomaly. Okay. So you can see that making an anomaly detection model, it's quite easy and quite fast. So you can make tests fast, and you can, from this point, you can improve quite a lot your model. And basically, what I have shown you with the fan, with this computer fan, it's the same exact workflow you will do with an industrial fan, for example, an air conditioner fan or something related to. Okay, so you can here like you can improve your model, or if you are happy enough with these results, you can go and deploy it. So let's see how the deployment works. There's a lot of deployment options. Well, right now there's only these deployment options because the Edge Impulse, your Edge Impulse account identifies that you are using an Arduino board, right? So I'm just going to change my camera so you can see me, guys. So there's a lot of different options you can use. There's different options you can try. You can, for example, download an Arduino library. Let's work with this right now. So basically what happens right now is that Edge Impulse converts the model to an Arduino library that you can upload into your Arduino. You can install it in the Arduino IDE and upload it to your board. As you can see, we have our Arduino library, but also you can make a really fast test deploying a binary. So I'm going to show you both options. So I'm going to create the binary. And let's go to the Arduino IDE. So I have the Arduino IDE right now. Let's just wait the binary to be done. I have a question here. For similar anomaly detection projects, but using other set of sensors, what do you recommend in order to build a representative data set? Well, that's a tricky question because it depends on what you want to detect and what do you want to define as an anomaly. But yeah, sensors play a big part into anomaly detections because usually anomalies are something that you don't want. So you have to you must have like really nice sensors in order to identify them. Okay. And also you have to, besides that, you have to have you must have really nice data to to train the model accordingly. So I will say it depends on the application and how complex the anomaly is. There's a question from to Marcelo from Amket. Sorry if I.
Well, I think the question is, no, I think he thanks for we show where the anomalies happen, no? When this, my question is, when did these anomalies happen? In time series analysis, this is very important. I mean, all the anomalies that happens when you are, for example, as Jose explained, for example, he prepared a data set that was when the fan was working properly, one time, and another the fan was in idle, not working. So it's anomalous conditions. Anomaly was when it put the paper or when it starts to move by fingers, was something that was not expected, or the data was not collect for that. So those are anomalies outside of the data set. You know? That is, I think this is the case. And then Jose said is, work with anomaly detection is very powerful because you don't know what's going on. And I think the example, no, Jose, was good. I mean, for example, the anomaly when Jose put the paper was completely different from the anomaly when he starts to run the fan with the finger. You can't preview such thing. But the model will say that it's not working, or oh, it's anomaly, it's not okay, something like, no.
Yeah, exactly. At what time? Well, the thing with the anomalies is that they don't happen like um they don't happen at a known time. They are random. Like that's why we want to do this and to predict anomalies. Well, I'm just going to show you. Well, I'm going to show you both ways. So if you have the Arduino IDE, you just have to install. I'm going to include the library. I just have it here. I have, what is the library? Oh, it's this one. Yeah, it's this one. So I just open, it's processing, and yeah. So this is in Spanish. It says library install. So we have now our library, and we can find it here on examples. And if you go here, on examples from custom libraries, you can find the anomaly detection demo SciTinyML-24 inferencing, sorry. So we have several examples for several boards. You can see that we have for an SP32, for a Nano BLE Sense, the Sense Rep 2. We're going to use Rep 1, and we're going to use the accelerometer continuous example. So this is really nice. I think this is one of my favorite features of Edge Impulse. But it's not working. I don't know why. Let's wait a second. I don't know if it's my computer or what is happening, but it should open right now the example. Okay. And also let's test the binary. Also, I'm going. This is the example. Okay. So you can see here that this is the example generated by the edge impulse that you can use it, but also, well, it has like a standard example, uh, but also you can use this example as a guide and develop your own code. Okay, so this is really nice. I think that if you are working on if you're working on customized hardware, this is really nice. This is a really nice feature. Um, also, if you just want to make a quick test, I'm just going to show you how to to do it. Just give me 1 second. Extract all. Extract. Okay. So this is the binary that I created. If you remember, I went here and select the binary, and what this makes is this binary that you just have to. Okay, yes, I confirm. Ooh, something happened with my Arduino Clear right now. Just give me a second as I fix the path of my Arduino Clear. If you have some questions right now, please leave it on the chat, and I will be really happy to answer that. I'm going to start, and this can take some time, so just let's be patient and let's talk about and let's answer some questions.
I think that you have a few questions about anomaly in the chat, Jose. No, the last ones is they are talking about Beatrice asked about if you can use anomaly to predict the possibility cause of the anomaly. I think it's related about other questions like how to take actions on anomaly if you do something in real time. So maybe from your experience with the engineer, what do you do with the anomaly?
Oh, well, that's a nice question. Well, I think it depends on the application and how complex do you want to be, do you want your system to be, or how fast do you want to react? Um, the thing with anomaly detection that it's the thing with anomaly detection is that there is no like one size fits all answer for most of the applications. Um, Regarding the can you use the anomalies to predict the possible cause of that anomalies? Yes, I think yes. But that's a yeah, that's a more complex model. Um,
But in fact, I
but
think that, for example,
yeah,
even if, in my opinion, I agree with you. But for example, if you have a model that works, that you did everything, and you tell your model, look, this is the nominal condition. Everything that happens inside this situation is okay. So everything that outside is not okay, so it's anomaly. So when you use this model, you can start to do tests in real situation, like the two one that you did today with a paper or a finger in a real environmental. You can see, for example, let's see if, for example, I have a bearing and I have a problem in a bearing. Let's see if I have a not correct position. So you start to test situations that can happen and see if this is considered anomaly or not. So I mean, so the model or such kind of a test model will help you to define what is anomaly. I think that it's something like that, not automatically, but help you to define your situation. No,
yeah, yeah. I
I
agree with
think,
you, Marcelo.
yeah.
How to take an action on anomaly? Is it real time? Well, not really. I think most of the times you want to predict an anomaly and to act before an anomaly happens. Because when an anomaly happens is because something is going to explode, for example, or the fan is going to shut down and you are going to lose a lot of produce, for example, if the fan is an important part of a cold room, for example. So usually anomaly detection, it's used more for predictive actions. Okay, so you can work before something bad happens to your system. I'm just going to show you. I just needed administrator permission. I just flash the binary on my H impulse board, and right now, what I am going to do is to open the H impulse daemon. As you can see, there's a lot of H impulse uses a lot of console, so you feel a little bit like a hacker using H impulse, and that's nice in my opinion. But I am not a hacker. I would like to be a hacker, but I am not a hacker. So I have here and oh, sorry, I
Jose, sorry a little bit. We have a question from Amhad. The hand is up. Amhad, you could tell your question.
yeah.
Amhad,
Um,
Mohammed.
I'm going. I'm just finishing right now,
Okay.
and I'm going to answer the question right now. As you can see, the model,
Okay.
the binary or the model, it's running right now in Arduino. It's running continuously, and you can see here the classification results. So right now the fan is turned off, so you can see that the probability that that is happening is quite high. And I'm going to turn on the fan, and let's wait that this is going to change. And let's wait. And yeah, right now the fan is working and something is happening. You can see here that nominal right now. Okay. So this is another way of making work the model on your board using the binary. And after that, I'm going to finish with the library, but this can take a little bit of time of compiling. So I'm going to answer some of the questions. I'm just
There is a question from Mohammed. So Mohammed,
yeah,
please.
Mohammed.
Amjad Mohammed.
Amjad.
So, yes. So let me rephrase my question, because in time series, the time is very important for the outlier. At what time did this outlier happen? Let us say that you register 2 time series and not one. One for the fan speed, but a second one for the temperature. And one says, if the temperature drops down to -0, let us say, then the fan will stop. So I use the second time series to predict the time series of the fan. I know now when will the fan stop. This is my question, actually. It's not usually in industry, it's not 2 time series, but one could get many time series, hundreds of time series, and one usually uses vector autoregressive analysis, VAR it's called, and Granger causality to see what are the connections between these time series. And in this way, one could predict that the fan will stop at this time because we have reached 0 degrees. We don't need the fan anymore. Thank you. Could one do this with this edge?
I am not sure. I haven't worked any anomaly detection models in that way. I don't know if you have made something similar, Marcelo.
Yeah, no, I mean, the
like
point
using...
is, for example, in this case, in this example here, for example, when Jose collect the data, he collected, for example, the data came from, for example, for 3 different sensors: accelerometer, gyroscope, and magnetometer. For example, he also could have a 51 that was a temperature sensor that was also send the information at the same time. I have a time series, and what Jose did was, first of all, he selected only, okay, I want only the information from the 3 axes from accelerometer. That's it. But he could have more. The point is, with time series, what we do with the first block, let's say this red block that we are doing here, we are doing windowing. So Amjad, what I'm doing is I took a window of, for example, a window of 100 milliseconds, of, in fact, sorry, a window of 200 milliseconds, okay? And in that specific window, he took the information from, okay, let's see the information of the accelerometers X, Y, and Z that was in meters per second, or accelerometer, sorry, will be in square meters per square seconds. And he could also add temperature on that. At the end of each one of the windows, what we have, it's a table, it's a tubular data. And this tubular data will be the input. I will extract some features from that, okay, like the average, I will take skewness, etc. And those features will be the input of my deep learning network, my network, you know. And what's happened is, if you take the information from the accelerometer plus the temperature and tell them, look, this is the nominal, okay, this is nominal, will be nominal. So go. Suddenly, if you have a kind of temperature and in this situation will tell you that is, for example, is not normal, not nominal. Okay, this you should take. So let's say again, when you take the window with the normal or nominal accelerometer plus the normal temperature. All this data will be create your data set, your features. In fact, from a raw data set, you have your features. This will be the input tensor of your model. You're training that. If during the normal operation, you are also collecting, so in this case, we will collect data from the accelerometer plus the temperature, and the temperature change outside for what you have training as nominal, you get anomaly. So the temperature will be outside of your cluster, okay, and you have anomaly.
Yeah.
I don't know
Thank
if
you,
you
Thank you,
Marcelo.
Marcelo.